starting from this pseudocode, we are going to learn how to translate our algorithm into a MATLAB code. Let's open a new file in the editor, and let's begin by defining the data. Let us define our first variable, the inflow rate qin. We can set it to 1. Notice how in MATLAB it is not necessary to explicitly state that the inflow rate is a number, unlike what happens in other languages like C or C++. But what is the text in green? So in MATLAB, what follows a % sign is switched off. It will be ignored by MATLAB, and it is just a message, a comment for us humans. Notice how we could also omit the semicolon at the end of this instruction. If we do this, and we run the code by pressing Run in the editor menu, the value of qin will be printed down here in the command window. And now we can continue to insert all the other data, so the area of the tank, the area of the outlet, gravity, the initial water level h0, but also the total simulation time, t, the number of time steps, n, and as a consequence, the length of the time step, delta t. And at the end, a double % sign will create a code section that we can run separately from the rest. So now we can run this section by clicking Run Section in the editor menu, and all the data will be set and ready to be used. And now we have to define the outflow rate. Do you remember that the outflow rate Qout is a function of the water level h? We need to write a piece of code that can take an input, h, process it, and produce an output, Qout. And this black box is a function, something that can take input and return outputs. In MATLAB, we can define simple functions using this syntax. After the @ the variable in brackets is the input of the function Qout, and it can be used in the definition of its output. And in this case, we are computing the outflow rate Qout using Torricelli's formula. But where is the square root? So in MATLAB, with the syntax hat, we can raise a base to any power. So in this case, using 0.5, we are computing the square root. Now, going back to the big picture, now that the function has been defined, we can run this section and it's ready to use. So how can we test it? We can print its output for a chosen input. In MATLAB, we can use disp to display a string, so some text on the screen, for instance. The outflow rate is. Then the value in brackets 0.5 will be given as an input to the function Qout to compute the result, which will be printed by disp. Running this last block, we obtain a value of about 0.31. Now we have all the ingredients to perform the actual simulation, and we want to store the values of h, the water level, at different times. For this purpose, we begin by creating containers called arrays. Arrays are order containers where we can store many values of the same type, typically numbers, but also characters or even strings. And each element has a precise position indicated by a number starting from 1. In our case, we need to create arrays of n+1 elements. And this syntax, zeros, is one of the ways to create an array of zeros, for instance, to store the simulation times. And notice that in MATLAB, arrays are always multidimensional, so we need to specify that we want one row and n+1 columns. We can do the same to create an array to store the water level h, and there we can fill the first position with the initial water level h0. And what about all the other values? We have a recipe to find h1 given h0, h2 given h1, and so on. So to compute all the other values of h, we need to learn how to write a loop. So to repeat a block of code many times, we can use a loop that begins with the keyword for. The n variable here serves as a counter to keep track of the cycles. And in this example, it takes values from 1 to 3 with a default increment of 1. So for a total of 3 cycles. And then we can write our instructions. For instance, we can print the value of n. And after the instructions, we need to close the loop with an AND. Now in the first iteration, we will print 1, and then 2, and finally 3. So going back to our problem, let's have a look at our algorithm. First of all, we need to find n values of h, because the first one is already known. And for a generic iteration, n, we know the value of hn, and we want to find hn plus 1. So first of all, we can compute the water level change in a time step depending on inflow, outflow, delta t, and area. And notice that the outflow rate depends on h. Then we can add this increment to the old value of h to obtain the new one, and we store the new one in the array in the correct position. And finally, we also save the corresponding time, which is n times delta t. So now, simply by running this short block of instructions, we are performing a very large number of operations. And finally, we will have all the discrete values of the solution h. And so now we can plot the solution. We can call the function plot with inputs times and h, respectively x and y in our plot. And here, the letter B in single quotes indicates the color of the line, so in this case, blue. So when we run the code, a new window will pop up, and it will contain the plot. We can also display a grid on top of the axis using grid on. And we can add axis labels, so times on the horizontal axis, h on the vertical one. So let's have a look at the solution we just computed. Notice how initially it grows very rapidly, but after some time it reaches an almost constant value. This happens because the outflow is initially small, but then it grows with the water level h, and eventually it matches the inflow, and we reach an equilibrium. And now it's your turn.